I have two water molecules right over here, and typically the water molecules, as they interact with each other, they form these hydrogen bonds. That's due to the polarity of the water molecule. We've talked a lot about that. They slide past each other. These hydrogen bonds give them all of these neat properties of water. But chemistry is much messier than sometimes our diagrams or explanations show. There's all sorts of crazy interactions. All of these things are bumping into each other in all different ways. And not only are the molecules bumping in different ways, but at any given moment, the electrons are jumping around. And on average, they might spend more time around the oxygen, forming a partially negative charge at that end and then a partially positive charge near the hydrogens, because the hydrogens are having their electrons hogged away from them. In fact, this is what forms the hydrogen bonds. But there's always constantly change there because they're all just jumping around. It's all very probabilistic. And so you can imagine, under just the right conditions, one oxygen or one water molecule might just graze this water molecule in the right way that these electrons get close enough to nab this hydrogen. But it doesn't nab the entire hydrogen. It doesn't nab the nucleus and the electron. And a typical hydrogen atom, actually let me draw it. A typical hydrogen atom is just a proton in the nucleus. Actually, the most typical isotope of hydrogen has no neutron. So it's just a proton in the nucleus and an electron orbiting around it. So this right over here is positive. Actually, maybe I'll just draw it that way. You have a positive proton, and then you have a negative electron. Orbiting around it. Actually, it's more of an orbital, so it's really this electron is jumping all around it. But you can imagine these electrons in this covalent bond, these were already being hogged. These were already being hogged by this oxygen. In fact, that's what was forming this partial negative charge over here and a partial positive charge over here. So these would be attracted to this partial positive charge. Remember, there you have a partial negative charge over here. This is actually, it's forming the hydrogen bond, and actually could bond to the hydrogen proton, while both of these electrons, including one of these electrons that used to be part of this hydrogen, or you could consider used to be part of that hydrogen, are nabbed by this oxygen. And in this circumstance, and I'm not saying that this happens all the time, but under just the right conditions, this actually can happen. And what would result, what would result is this thing over here, instead of just being a neutral water molecule, would look like this. So you have your oxygen, you have not only your two hydrogens now, you now have a third hydrogen. So you have these two covalent bonds, this lone pair. And now this lone pair, which I have circled in blue, is now being shared with this hydrogen proton. This electron right over here of the hydrogen got nabbed by this oxygen. So now you formed another covalent bond. And now this character over here, he's lost the hydrogen proton, but he's kept all of the electrons. So this character over here is going to look like this. You're going to have your oxygen is still, and now it's going to only be bonded to one hydrogen. Has these two original lone pairs. Right over here, and then took both of the electrons from this covalent bond. And so it has another lone pair. So this molecule gained just a proton without getting any electrons. So if you do that, you're now going to have a net positive charge for this one over here. And this molecule over here, actually let me just write it. I want to write it a little bit neater. And this molecule over here, so we have this molecule plus this one. This one gained this one lost a proton without any other changes, so it now has a negative charge. So just like that, you went from two neutral water molecules to two ions. And these ions, this one over here, the one on the left, the one that is now H3O, and it now has a positive charge. Actually, I put that O in a different color. H3O. It's a positive charge. This is called the hydronium ion. Hydronium. And this one over here, that is OH minus. So it's OH. Let me get the colors right. OH minus, This is called the hydroxide ion, or since it's negative, you could call it an anion. But I'll just write hydroxide. Hydroxide ion right over there. So you have this water, and it's just kind of automatically under the right circumstances. This isn't happening a lot, but under the right circumstances, you could have one of the water molecules nabbing just the hydrogen proton from another water molecule, and that water molecule is going to keep both of the electrons, and then they ionize. They have autoionized. And this phenomenon, this is called the autoionization of water. Let me write that down. It's a nice big word. Autoionization. Autoionization of water. And I really want to make it clear what happens. This hydrogen over here that you can imagine at first was a proton and an electron. The typical isotope of hydrogen actually does not have a neutron. But then this electron got swiped. This electron was part of this bond, and it gets swiped away. And so all you're left is with this proton, and this proton goes to this other water molecule, giving that a positive charge. And so you might say, well, how frequently would I find hydronium ions in water? Well, the concentration, let me actually draw a little tub of water here. Let's say this is a liter of water. This is a liter of water. The concentration of hydronium in typical water, the concentration of H3O, the concentration of H3O in typical water, and you put brackets around something to denote concentration, is 1 times 10 to the negative 7 molar. And molar, this just means moles per liter. This is the same thing as 1 times 10 to the negative 7 moles per liter. And now you might be saying, well, what's a mole? Well, I encourage you to watch the video what a mole is, but a mole is a quantity. It's like saying a dozen, but it's a much larger. A dozen is equal to 12 of something. Mole is roughly equal to, let me write it, a mole is approximately equal to 6.02 times 10 to the 23rd. 10 to the 23rd of something, and you're typically talking about molecules. A mole of a substance means approximately 6.022, it actually keeps going, times 10 to the 23rd molecules of that thing. So you might say, hey, 1 times 10 to the negative 7 times 6.02 times 10 to the 23rd, that would still get us, let's see, this, let me write it down. 1 times 10 to the negative 7 moles per liter times, I'll do it this way, times 6, I'll just go with 6 since we're going to go approximately. So approximately 6 times 10 to the 23rd, 6 times 23rd molecules per mole, well, these two would cancel out, and you would multiply these two numbers. You would get 6 times, let's see, 10 to the negative 7 times 10 to the 23rd. That's still going to be 10 to the 16th power molecules per liter. Molecules per liter. So your first reaction is, oh my God, I'm going to have 6 times, or roughly, I'll say roughly, approximately 6 times 10 to the 16th molecules of hydronium in this. That's a lot. We should see it all the time. But we have to remind ourselves there's just a lot of molecules of water in there as well. In fact, a liter of water is roughly, so 1 liter of H2O contains approximately 56 moles of H2O. So one way to think about it is I have one time, and if I'm thinking about a liter of water, I'll do it over here. I have 1 times 10 to the negative 7 moles of H3O for every 56 moles of H2O. So if you look at this ratio, then you start to appreciate the ratio of 1 times 10 to the negative 7 to 56. Let me do it down here. So this is the same thing as 1 times 10 to the negative 7 to 56 is the same thing as, let's just multiply both sides times 10 to the or the numerator and the denominator times 10 to the 7th. So if we do that, this is the same thing as the ratio of hydronium to regular water to H2O is going to be 1 to, see if I multiply 56 times 10 to the 7th, I'm going to have 5, let me get right in that same color. I'm going to have 5, 6, and then I'm going to throw 7 zeros at the end of it. Let me do that. 1, 2, 3, 4, 5, 6, 7. So the ratio of hydronium to regular H2O is 1 for every 560 million. So even though you might say, oh wow, look, we have a huge number of molecules of hydronium in this liter of water, for every one of them, you actually have roughly 560 million molecules of H2O. So that should give you an appreciation for the fact that this isn't that typical. In fact, you're going to see this much more often than you see this over here. In fact, if you wanted to make these arrows kind of show which direction the equilibrium sits in, it's actually much further. It's actually much further to the left, so we could make this arrow much bigger. But it also gives you an appreciation for just how many molecules you have sitting in a liter of water.